Right. All right, so today we're going to carry on with our reviewing from Calc 1. This shouldn't take too much longer. We're going to carry on with our review of integration today. We'll be looking at the basic rules of integration, and that might take up the whole session. It might not. We'll see how that goes. If not, we'll certainly have it finished next time, and then we can dive into the new material, which is Chapter 7, which is applications of integration. So it's a good tie-in to go directly from our review of integration to Chapter 7, I think. So anyway, so let's get back to where we left off. So remember, I posted slides from Calculus 1 here. What we're looking at now is Chapter 4. And so what they're doing for us here is introducing us to the idea of integration, which is, of course, the reverse of taking the derivative. And they're introducing us to some notation here. And here they've summarized some of the basic formulas that we'll be needing as we go along. So you can see, for example, the derivative of a constant is 0, which means the integral of 0 must be a constant of some kind. Remember the rule k, the k is a constant, by the way. The derivative of kx is simply k, which means the integral of k must give us back the original kx. Now, also don't forget about this part of it. Whenever we integrate, unless we're given more information, we need to include this constant because there's an entire family of functions that actually will give us back the original derivative. So we will need the constant for these cases. Now, keep in mind too, these are what we call indefinite integrals, where we're not given any further information. With definite integrals, we don't need the constant because we will end up with a numerical result. But here we're starting out with indefinite integration. So we will need these constants. So here they're reminding us that, for example, constants can be moved outside of the integration symbol. And so that way, instead of trying to do kf of x directly, it might be easier to keep the constant on the outside and then integrate f of x itself directly. We also see here that the integral of a sum is equal to the sum of the individual integrals. And then here's one of the more important rules. We see this all the time. If you have the integral of x to the n power, the integral is x to the n plus 1 power over n plus 1, except in the one case where n is equal to -1. So in other words, if you have the integral of -1, or of course 1 over x dx, this gives us back the natural log of the absolute value of x plus c. All right. So, and of course, with the trig integrals, we're basically just reversing the process of differentiating them. For example, since the derivative of the sine is the cosine, it means that the integral of the cosine must be the sine, with the c, of course. Never forget those little c's. And now here, for example, if the derivative of the cosine is the negative sine, the integral of the sine of x must be the negative cosine of x. And then you can see they're going through the entire list here. They're simply showing you that integration is the reverse of doing differentiation. Let's see. So they got a few examples for us here. For example, the integral of 3x dx. Let's move this over here to my notes sheet. So first we notice that we, of course, have the ability to move the 3 outside. Now, also don't forget that x is the same thing as x to the first power. So that means that we're using basically two rules at once. Right here, this rule at the bottom, the power rule, x to the n is now going to give us back so in other words, remember, x to the n, the integral of x to the n dx equals x to the n plus 1 for n plus 1. Unless, of course, n is -1, which it most certainly is not here. So that means that the integral of x to the first power is simply x squared over 2. And you can leave it like this. You can simplify it a little, but don't forget the constant at the end. All right, what else do they have for us? Oh, now this one looks kind of tricky. Sometimes I think what they're trying to do here is make the point that sometimes you can take these horrible looking integrals and actually simplify them with simple algebraic steps. And I think that was their intention here, because when you first look at this, you might think, oh my God, what are we supposed to do with this one? And in fact, the thing about integration is the biggest challenge really is recognizing which approach you're supposed to use, because there's so many to choose from. That's why, as you'll see later on, the list of integration, the integration tables at the back of this book are several pages long. And there's a reason for that, because there's so many different integration rules that we may need. So we've got x plus 1 over radical x dx. And at first glance, you might say, I don't know what to do. So you might also then say, well, maybe let me try a little algebra to speed this up a little. Let's try this. Certainly, that is a valid statement. I'm splitting it up into two parts. Now, of course, recalling that the square root of x is x to the 1/2 power. It's just another way of writing radical x, or actually, in this case, I'm going to leave it as x to the 1/2 power. So we've got x to the 1/2 power. Now, the second one, 1 over radical x, is the same as x to the negative 1/2 power. Okay, so in other words, the original expression, this really awful thing, can be simplified to x to the positive 1/2 power plus x to the negative 1/2 power dx. Now, I can use my rule terms individually and then add them up. Okay, we did see in the list that the very bottom, we know how this rule works. Where are we? Right here. And then, of course, we also are actually using this one as well, because we're taking two terms and adding them together. So here's what we end up with. The first term will be, so 1/2 plus 1 is 3/2. 1/2, negative 1/2 plus 1 is 1/2. Now, of course, these are very messy expressions. We don't want to just leave them like this, do we? No. Okay, so we'll rewrite this as 3/2 x to the, sorry, 2/3. Have to invert it, of course. And that is our final answer right there. So we dodged a bullet with that one, I think. Now it's possible. Of course, there's always multiple ways of getting it any result in math. And I'm sure there's another technique we could have used, but I think you'll agree that this is very straightforward, because you're reducing it to something that's more manageable, I guess you could call it. And so if, whenever it's possible, you may want to try this whenever something looks really scary at first. Reducing it with algebra can often bring us closer to a result. It's not always possible, of course, but we can give that a shot. All right, so yes, the integral, this indefinite integral, as it's called, has an infinite number of possible solutions, each different by a constant. Okay. Um, and you can see they've got a nice little graph here where here's our original integral. All of these curves um, the derivative will always give us back the original 3x squared minus 1. So, like for example, what they're getting at is, let's say you have something like this. Here's your expression. But if I had a constant added to that, No matter what that constant is, the derivative is still x plus one because the constant has a derivative of zero. So in other words, that's why when we integrate, we have to allow for the possibility that there's a constant that we don't know. It could be zero, but it doesn't have to be. So we're going to leave it like that. And without further information, we just leave it as a constant. Now, let's see. Let's try this one. 3x squared minus 1. Okay, so you can break this up into two pieces. We can bring this constant on the outside. And so using our favorite rule, we end up with and by the way, when I break it up like this, I've actually got it. Technically, I have a constant for each one separately, but the two will cancel each other out. Or they can be, I'm sorry, they can be consolidated into a single constant. Okay, so we can simplify it a little. In fact, if you wanted to, you could think of this as C1 and C2. So you've got x cubed plus C1 minus x plus minus C2. So you also end up writing it as x cubed minus x plus some constant C, which we don't know what it is anyway. Okay, so that's our final answer. Um, okay, and by the way, you can always double check these. If you were to differentiate this, which is what they're showing us in the next part of the slide, you'll see that it does in fact bring us back to the original function, 3x squared minus 1. Okay, good. That means we must have done it correctly. The constant is irrelevant. We know that it drops out, so it doesn't matter what the constant was. All right. Now, this is a little different now because all of a sudden they're telling us that we know for a fact that x equals 2 and y equals 4 are on the function that we're looking for. So let's say, let's see, what are they doing here? If they give us the integral of 1 over x squared we could let's see what are they doing. So what they're telling us is that we know for a fact that x equals 1 is on this curve. In other words, you can see the result here is actually an infinite family of curves, all of which satisfy the integral, but only one of them. If we know the one we're looking for, they're telling us that we must include the point 1 comma 0. So what they're having us do is say, well, all right, here's what you do. If you replace the x with a 1 in your answer, that is, oh, wait, sorry. No, they're telling us that the point is 1, 0. So in other words, I missed that part. Capital F, remember, is the integral. So they're telling us that capital F of 1 is 0. So now that means x is 0. X is 1 rather, y is 0. So that means that 0 equals x to the minus 1 or negative 1 over x. So I'm going to replace the x with a 1. So that means we're being told that the specific constant for this case is 1, because we know that this point is part of the solution. So that means that this integral can be rewritten as minus 1 over x plus 1. Let's see. In other words, we know the identity of the constant. Okay, so that uniquely identifies our solution. It's this curve right here. It could have been any one of them, but by giving us this information, we're being told that it must be this curve. All right. Anyway, so by the way, when we do this, this is called definite integration. I'm sure they're going to show us a million examples of this. Indefinite integration means we don't know what the constant is. Definite integration means we know the actual solution. So here they're asking us to do this as a practice problem. Negative 9t squared. You see, this is exactly like the ones we've just been doing. Plus 14t minus 2. Oh, sorry. I made a mess here with my notation. This should be every once in a while it gets like this. It's refusing to erase. That's better. I want to make it a little clearer. There we go. It's negative 9t squared plus 4t minus 2 dt. So you can break it up into 3 separate integrals. I'm just automatically moving the constant to the outside. Okay. And then, with the understanding that each one individually has its own constant, we can just consolidate them at the end. We end up with minus 9 e cubed over 3 is 14. E cubed is squared over 2 is 2t. And then we just simplified a little bit. Don't forget the constant. And then we'll have all right. And again, if we feel so inclined, we can double check by differentiating it with respect to t. And that's where we started at. Okay. No problems there. Okay, very good. All right, so what's next? So the actual answer, of course, is the negative 3t cubed plus 7t squared minus 2t plus c. This is our double check right here. All right, great. Now, all right, well, we don't need to do every single one of these. Let's go on to the next one. Oh, that was it for that section. Okay, great. This is section 4.1. Let's try 4.2. Area. Now, this is where they're trying to get into what exactly the integration process is giving us. And we may recall that the integral can be used to find the area under a curve over a given interval. And so here they're starting out with summation notation. So you've got a series of terms, n of them, as a matter of fact. And so this is our summation notation or summation operator. And whenever you see something like that, it means you're going to add up something. Okay. The variable itself will be indexed, in this case with an I, and that tells me that there'll be n terms, indexed from 1 to n. By the way, here's an interesting side note. This is the Greek letter sigma, but specifically it's the uppercase sigma. This is the lowercase sigma in the Greek alphabet. seen it many, many times. We've never had a course in statistics, that's for sure. All right. So anyway, this is used to represent summation. Now, by the way, the summation operator is more general than this. You can use it to increase, or the index can actually be organized any way you like. It can start at any number. It can end at any number. It can go all the way out to infinity. But there's also a way of adding the indices so that it's not necessarily one at a time. You can actually jump ahead by two or whatever number you need. But here we're doing the standard approach. I equals 1 to n means 1, 2, 3, 4, 5, all the way up to n. In many cases, though, we do need to start with 0. That's not that unusual. Sometimes we need a negative index, but most of the time, either we'll be using I starts with 1 or it starts with 0. So now also, if you notice that here we've got a function of j squared, so you have to make sure that each of these is actually squared before you add them up. And yeah, you can see they're getting kind of messy here. But you'll see why this is so important. We'll get back to this in chapter 9, and you'll see that this gives us a lot of extremely important results. Just a few quick reminders. When you have a constant here, you can move it outside. Um, just add up the a's, and then at the end you can just multiply by k. Here you notice how the sum of either a sum or a difference can be broken up into two separate sums. If you have a constant, it can just simply be moved outside. Now this one is different because you're essentially multiplying c by 1 through n. Okay. Now, by the way, here's some interesting results that will come in handy later on in chapter 9. The sum of I from 1 to n is actually equal to n plus 1 over 2. So in other words, if I wanted to add up the first 100 numbers really quickly, oops, sorry. I could sit there and actually do it 1, 2, 3, 4. But having this formula in my knowledge, it's 100 times 101 over 2. Wow, that was easy. Now, let me give you a little insight into why this is happening. When you've got 100 numbers like that, all in a row, here's what's actually happening. You can think of this, and we're trying to add these up. You can think of this as here's a pair of numbers that adds up to 101. And here's another one. And here's another one. So if I wrote out all the numbers, you can see we actually have 50 pairs of numbers that add up to 101. So we write out this formula. Reduce it to 50. And so there's a logic behind this. You've got 50 pairs of numbers that add up to 101, and their product, of course, is 50-50. Interesting. So anyway, so they all have their own internal logic. I squared gives us this one. So if you needed the first 100 numbers squared, you could do it with this very surprisingly simple formula. And then I cubed, you've got one here. I don't know if there's one for either the fourth. There probably is, but it's probably very complicated. But you often see these listed in tables in a calculus book because they can come in handy with what we need to do in chapter 9. Ooh, now sometimes what you can do is take these awful looking results and simplify them. You can do like we did before, take it and break it up into something a little bit simpler that might look like one of these cases. So this by itself is going to be a nightmare. So what they're recommending we do is break it up. Now the n is a constant, so we can move that on the outside. And now we have a formula for the sum of the i's, but not I plus 1. Not a problem. We already know that one of the properties of the summation operator is that we can break this up into two sums. Oh my God. So look how this is a very clever result, I must say. Um, very clever. After a while, when you get used to using the summation operator, you start to notice these things yourself. But at first, it takes a while to get used to this. So let's just run through it one more time. It's I plus 1 over n squared. So the constant n 1 over n squared is outside. And then we break this up into two sums. Oops, that's 1. So 1 over n squared is just 1 over n squared, whatever that happens to be. This term we've already seen as n plus 1 over 2. Now this is a constant. Instead of Cn, it's 1n because that's the C from this expression. So we've got and here you can simplify. You can see, for example, both of these terms have an n in them, and I'm not sure what good that does, but you can rearrange it algebraically, but we're done here. So once you know what n is, you can easily figure out the sum. And so this is what they're encouraging us to do, to use our cleverness. Okay. Now, areas. Well, we know how to calculate areas. So we can skip over all this, but here's what they're trying to show us. Here's a curve. The function is negative x squared plus 5. So how do we figure out the area under that curve? It doesn't have a specific shape. It's not necessarily a circle or any of the other standard shapes that has a formula. So instead, we can use this approach where we create a series of rectangles inside the curve. Now, if you notice, the intervals they've chosen are 0, 2/5, 4/5, 6/5, up to 10/5. Now, the problem with this approach, though, is that what do you do about the height of the rectangle? Well, here in the left diagram, the height of the rectangle is determined by the right endpoint of this interval. Whereas here it's the other way around. Okay, so in other words, there's two approaches to doing this. In the first case, we're taking the height of the rectangle from the right endpoint of each interval. In the second case, it's the left. And you can see in the first case, we're understating the true area. In the second case, we're overstating it. So the strategy here is to shrink up the width of these intervals. If we have more rectangles, the area will get closer and closer to the correct area under this curve. And as a matter of fact, if we do this in both cases, on the left and the right, we keep shrinking up the intervals. The two sides will eventually converge to the same result, which is the area under that curve. Now, I don't know if they have a diagram showing that. Oh, I see what they've done. They decided to combine the summation notation so that we can get an approximate area under these curves using the ones you're seeing here. Now, you could do these separately or you could add them up. And what they're showing you here is that this is the one that understates the truth. This is the curve on the left. This is the width is 2/5 in each case, but the height If you think of these as I equals 0, oh, I'm sorry, they're using 1, 2, 4, and 5. We represent these 5 intervals. And the right endpoints are what they're interested in now. Okay, that's this case. This is the right endpoint. This is, of course, the left endpoint. So starting with the one here. So if that's the case, the formula for determining any of the right endpoints, given that the index I runs from 1 to 5, it's simply 2/5 I. Okay, so that's what this is all about. And so therefore the sum can be thought of as the widths are always 2/5. The height is a function evaluated at the right endpoint, which is what I mentioned over here. So in other words, f of this right endpoint is the height of the curve, of rectangles, sorry. So therefore, what they're saying is, well, the function itself is minus x squared plus 5. So therefore, within here, we're going to have minus 2i over 5 squared plus 5. That's for the height of each rectangle. And then the width is always 2/5. So they're using the results we had earlier to come up with this number. For the the left hand points, the height of the rectangles is, in this first case, it's 0, then it goes to 2/5 and then 4/5. So they're going to write that as 2/5 I minus 1. Okay, so in other words, for the first one, it's actually 0. So that's why it's different. So the two are slightly different. 2i over 5, 2i minus 2 over 5. Okay, so anyway, so the point of this is that they're using geometry, they're using the areas of the rectangles indexed by I to come up with the approximate area under this curve in 2 different ways. They're first using the right endpoint approach and then the left endpoint approach. And they're using our summation rules to come up with the approximate area. Okay, in other words, they didn't sit down and do all 5 of these and add them up. They're using the rules from back here. Now, as I said, I mean, of course, you can see for yourselves this is not correct, and the two are not the same, and that's not a good sign. So what we're going to do is use limits to get closer and closer and closer to widths of 0 for these rectangles. And as we keep shrinking up the widths of these rectangles, eventually the two sides will match, and they'll be exactly equal to the area under the curve. And this is what integrals are really all about. An integral ultimately is an infinite sum. So yeah, here's this curve. It's closed on the interval AB. And any random rectangle is going to have a width of b minus a over n, because we need to break it up so there's n rectangles. And the height of the rectangle can be thought of as either okay, it looks like what they're trying to do here is have the left endpoint is lowercase mi, the upper is capital Mi. Oh, that's all it is. Okay. So these are the endpoints. And this is what we were saying before. You've got the sum that comes from the left hand, or in this case, we're calling it a lower sum. Oh, I forgot to mention this part. In English, oh, let me go find it. The correct names for these two. No, I can't find it. Sorry, hold on. Oh, okay. So this is what they're telling us. The case on the left of this diagram, these are said to be inscribed, and these are defined to be circumscribed. All right. Just in case, if they keep using this terminology, we just want to make sure we know what they're referring to. The one on the left is formally defined as inscribed. The word inscribed can mean a lot of things. So I guess in this specific case, inscribed means all the rectangles are completely contained within the curve. On the right-hand side, it's the other way around. So the one on the left is called a lower sum. Let's write that in here as well. And then this is defined as an upper sum. And then the actual sum, of course, is in between. So, here's another example where here the rectangles are all underneath the curve, here they're all above. And of course, that's because of the way they're calculating the area, whether it's based on the lower or the upper interval or endpoint of each of these intervals. So, they would like you to, oh, now they're labeling them. Okay. To add these up, and I guess using our clever strategies from the summation notation. But yeah, oh, okay, here we go. So this is what we're building up to. N is the number of rectangles. As the widths decrease, the number of rectangles increases, of course. As we approach an infinite number of rectangles, the limit of the sum, whether we're using the inscribed or circumscribed rectangles, is going to be the same. And that is the sum or the area underneath the curve. Okay. So yeah, we don't need to dwell on this too much because I know we've already seen this before. But and they're also saying, by the way, if you just want an approximation, you could just look at the center of each of these rectangles and you should get something halfway decent. So what we should probably do is move on to the actual rules. This is 4.2. Comes 4.3 eventually. There it is. Usually the one I ask for, it pops right open, but I guess not here. Anyway, we're going to start by introducing this concept of the Riemann sum. And, again, we're using the same setup. We've got all these intervals, but now all of a sudden they're not all the same, are they? So the delta axis can be different for each of these rectangles. And there's a pattern there. The pattern comes from n. N itself is the number of rectangles in this interval. So here we're assuming C is the right endpoint. And so this limit is equal to, now the f of C is the height of each rectangle. The delta x is the base. Remember, the area of a rectangle is height times base. So what they want us to do is consider this curve, f of x equals the square root of x, over the interval from 0 to 1, where the left endpoints are I minus 1 squared over n squared. The widths will be 2i minus 1 over n squared. Now they're going to use the summation operators that we used earlier. We're going to rearrange this and solve for it. As you can see, they've got 2i squared and they have negative I. We know how to solve for those. The n is a constant. And so you can see what's happened here. We've got this result, again, based on the summation operator's properties. But if you notice the limit n goes to infinity, the number of partitions or rectangles is converging to infinity. So if you remember from Calc 1, when you calculate the limit of a polynomial, if you have the variable in the denominator, this is just 0. Because you're assuming that the denominator is becoming enormously large. So the entire ratio is converging to 0. But the limit of a constant, no matter how you slice it, is equal to that constant. So the sum is 2/3. So what they're claiming here is that using this approach, we can prove that the area under this curve is equal to 2/3. Now, we can use this approach if we want to, but in practice, what you would normally do is take the integral of this function over the interval from 0 to 1 to come up with your answer. It's nice to know the definitions that are going on behind the scenes, but for all practical purposes, we're going to do these with integration. So in other words, if you wanted to double check this one, you could say, well, listen, let's make sure they did it correctly. So the function was radical x over the interval from 0 to 1. So what we're actually going to do here is do what's called a definite integral. We're not just integrating it, but we're also going to evaluate it between those two endpoints. So we're going to have, let's rewrite this as x to the 1/2 power. Now, this part, the notation can be very different from one book to the next. The way I'm used to seeing it is right like this, which means we're going to evaluate it in a very specific way. And first, let's simplify it a little. And, we can move the constant outside and treat it separately. So the way this notation works, what you're being told to do is this. You're evaluating this function when x equals 1, then you're doing the same thing for 0, and then you're subtracting. right? This is how definite integration is carried out. So we're going to have, and when you get out, it's the same. Okay. So yes, so that this is how we can do it with our definite integrals. The theory is great. It's important to understand what's happening behind the scenes. But as far as getting actual results, we're probably just going to stick with the rules of integration. Now, if you find yourself moving on down to more advanced math classes, eventually you'll be asked to do proofs, and then you really have to understand how these results come about. But for right now, we're gonna, of course, understand, but we want to use the rules. Um, the proofs can come later. Okay. All right. Why don't we, here we go. So now, of course, as you've already seen, the integral itself is actually nothing but a limit. The limit of the area under that curve as the number of partitions or rectangles goes to infinity. So if we're integrating over a specific interval, here it's the closed interval a to b, we use this notation. And you could think of these as the lower and the upper limits of integration. And they're going to tell us that, by the way, continuity implies integrability. In other words, as long as the function is continuous, that guarantees that we can find an integral. So no, now they're giving us an example. All right, let's try this one. Now we're not going to use the Riemann integrals. We're not going to use the rectangles. We're just going to do this directly with the rules of integration. They want us to find. So this one's pretty straightforward. I mean, what are we doing here? See, we have an issue here because some of it is below the curve and some is above. So what that means that -3 can't be right. Um, so I guess I don't know why they picked this example, but so what you can do is break it up into two pieces and integrate each one separately if you need the actual total. But if you apply the integration directly, you're going to get and something's wrong there. So what you would have to do now is to get the area here, integrate from sort of one. Whoops, sorry, I left out the two. So this area is one, and this piece. Now, again, it's negative four. It's not, it's actually four because it's under the axis, but four is the actual area of that rectangle, triangle rather, because you can see that the triangle has an area of 1.5 base times height. So this one happens to have um, a base, actually the height, even it's upside down, but it's the height is four and the base is two. So the actual area is four. It's not negative. It's only turns out it comes out negative because it's facing down. It's underneath the horizontal axis. So since the actual areas of these two are four and one, the total area is actually five. Okay, but if you just integrate it directly, you see what's happening is you're getting positives and negatives offsetting each other. Okay, so wait a minute, what happened? Oh, so they're moving on to another example. All right, then. This time everything is above the horizontal axis, so we won't run into that problem. The curve is 4x, the function is 4x minus x squared. They want to evaluate it, or in this case, integrate it between 0 and 4. All right, let's give that a shot. So we have 0 to 4. 4x minus x squared. And they've already given us, shown us what it looks like. It's a parabola that's facing down. And the height is 4. So we can break this up into two separate integrals. Okay. Okay, so first let's do a little simplification. 4 and the 2, 4 divided by 2 is of course just 2. Actually, what I could have done is move the 1/3 outside. It's not that important, but I guess to be consistent, maybe that's what I'll do. All right, let's see where we get where this takes us. So that's going to leave us with now we need a common denominator. Let's make that 96/3. Okay. So, oh no, that's the answer. What was that all about? Well, all right. Well, we got the answer. It's just, usually they give us now. Here's an interesting one. It's just a rectangle. It couldn't be any simpler. Ooh, not so simple. This is a trapezoid. Who remembers the area of a trapezoid? Well, we can certainly look that up. But here's some interesting results. And this gets back to what we were doing before, by the way, this discussion about what to do when the function is underneath the horizontal axis. If you notice here, f of x dx, when the interval is from a to a, it's just zero, of course, because what you effectively have there is a straight line which has a base of zero. But here, and unfortunately, this seems to be a typo. This was supposed to be a b. Oops. Yeah, sometimes the eraser doesn't work very well on this thing. Okay. Well, technology lets me down every day anyway, so it's just a question of when. Okay. So in other words, basically what it's saying is that if you reverse the upper and lower limits of integration, you'll end up with a negative of the original result. So um, if you go back to that example we had before, when I break this up into two parts, because some of it is underneath the horizontal axis. Let's see, let's copy this down here. 2x dx. To get both positive results, what we could do is this. So it could be rewritten as Oh, what did I do? Sorry, I substituted in four. It's -2. No wonder it's not right. Okay, that's better. Phew. All right, so it's 4 - 0, which is just 4 plus 1. Well, well, well. Okay. So let's see, where did that leave us? What's next? There's only maybe one more four. Oh no, there's two more. All right, let's just go to what's coming next. Oh, okay. We're getting into some very deep waters here. Maybe we'll hang on to this until the next time. But when that's done, basically, what they're showing us is that this integral is really, let's see if we can draw this properly. Now, remember the capital F's are the result of taking the integral. So um, you could calculate this just by calculating the integral of the two endpoints um, and subtracting, and you'd have your area. But anyway, yeah, so we'll get, I think we'll save this for next time. We don't want to rush through it. And then 4 - 5, substitution. Wow. Now, this is an important technique, or sometimes it's called U substitution. Very, very helpful. It's essentially the reverse of doing the chain rule with the differentiating with the chain rule. So, but it does take some recognition to know, oh, this is an appropriate time to use this U substitution. So, it's awfully useful, though. It's awfully important. We'll see it quite often. So we'll do this. And so in our next session, we'll go through this as well. Don't want to rush through this either. And then finally, at long last, we can start the new content in chapter 7, which is essentially like it says in the title, just area of applications, sorry, of integration. So usually they're all kind of taken from physics, but they can be very interesting. So we'll run through this, make sure we don't forget how this works. And oh, there's our favorite rule, or the power rule. Except this time it's g of x instead of x. And so we're going to need to use this type of technique. So all right, so this will be it. This will wrap up a review of Calc 1, and then we'll start the new material in the session after that, probably. So, all right, I think we got a lot done today, that's for sure. So I'll see you all next time.